The last problem that you're going to work on today is this problem, deducing a rate law from initial reaction data. So this is a lot like the stuff that we were practicing in this section 19.4. This we have three different reaction situations. We've got reaction 1, 2, and 3. And in these different situations, we have changing concentrations of our reactants and changing rates, and our job is to try to figure out what the rate law is in this form right here. K, N2 to the X, H2 to the Y, and we're trying to solve for X and Y in the rate law. That's our goal. So this problem is actually quite a bit trickier than the ones that we were doing, because the changes that are being made are not working out to be nice even changes. Like, we're not exactly doubling or exactly halving or something like that. It's close to, this one looks like it might be 1/4 going from here to here, but if you punch those numbers into your calculator, it's not exact. And unless it is exactly doubling or exactly tripling or exactly 1/2ing, we cannot just make in our head quick calculations of how that's going to affect the rate. We have to be more mathematical about it. So that's what we're going to do in this problem. So our first job is, let's just go ahead and start by tackling X. And if we're trying to solve for X, that means that we want to look at two sets of data where H2 is not changing. We want two sets of data where H2 is not changing. So that's going to be data set 1 and data set 2. And this is going to allow us to focus just on N2. So what we're going to do is write two rate laws for reaction 1 and reaction 2. And I'm just going to fill right in. So the rate for reaction 1 is 6 times 10 to the 5. I'm leaving off units to save space. And that is equal to K times our N2 concentration, 1.76 to the X, 2.19 to the Y. And then we're going to do the same thing for data set number 2. Our rate is 1.44 times 10 to the 5. And that is equal to K, the rate constant, times 0.422 to the X, that's our N2 concentration, and 2.19 to the Y. And what we're actually going to do here is make this into a fraction, like two fractions. So I'm going to see if I can we're going to do it like this. I wonder if I can, trying to do something really high tech here. Move this over. I can. How cool. Okay, so we're going to make this whole equation into just one big massive fraction. And I'm going to make sure that the 1 and the 2 are not confusing there. So we've got a huge fraction that we're going to use to solve for X. And the reason that we're doing this is because we can say, well, on the right-hand side, 2.19 to the Y divided by 2.19 to the Y is going to be just 1, so we can ignore those terms. And we don't know what K is, but we know that K divided by K, it's going to cancel itself out. So we can simplify so that it is 6 times 10 to the 5 divided by 1.44 times 10 to the 5 is equal to 1.76 over 0.422 to the X. I just did some awesome exponent math right there. So before we get crazy, because we've got to solve for X and it's up in the exponent, which is a bad place for it to be. Before we get going on that, let's just work the fraction math out. 6 times 10 to the 5 divided by 1.44 times 10 to the 5. That is 4.167. And 1.76 divided by 0.422, that is 4.17. to the x. Oh, this one's worked out easy. We can just see that. We can see what it's going to be. But let's pretend like we couldn't. Let's pretend that we couldn't see. If I have less sig figs on here, it makes it easy. We can see that x is 1. Let's pretend like we couldn't see that x is 1, and we needed to solve for that. We would use either the log or the natural log of both sides. And that allows us to drop that exponent down like that, and then you could work the math out on that, and you're going to get x equals 1. So we've got that part of the rate law figured out, and to the 1, which ALEKS probably doesn't want you to put that 1 in there. So now let's go back to our data set and figure out how we're going to solve for y. So when we're solving for y, we're looking for two sets of data where n2 is not changing. So that is going to be data set 1 and data set 3. We want to set that up like a fraction. So data set 1, the rate is 6 times 10 to the 5, and that is equal to k n2, which is 1.76 to the x, and 2.19 to the y. And then our data set 3, that rate is 1.3 times 10 to the 7, and that is equal to our rate law k times 1.76 to the x and 10.2 to the y. Now you might be saying, well, we know what x is. Why aren't we plugging x in? Well, whatever x is, we're just going to cancel it out. So why bother actually plugging it in? We're just getting rid of it. So now we have some math that we can figure out. 6 times 10 to the 5 divided by 1.3 times 10 to the 7 works out to be 0.04615. I'm leaving a lot of sig figs on there. And that is equal to 2.19 divided by 10.2. That is 0.2147 to the y. So here's one where we are going to want to use our log properties. Log of 0.04615 is equal to y times the log of 0.2147. Another thing that you could do is just start guessing and checking. You could just start plugging numbers in for y, remembering that these exponents are like 0 and 1 and 2 and things like that. Log of 0.04615 divided by the log of 0.2147. That gives us a y of 2. So that means back over here to our rate law, we know that the coefficient for H2 is 2. And the last thing that this problem is asking you to do is solve for the rate constant k. So now that we have the rate law, we can pick, totally up to us, we can pick any one of these 3 sets of data and plug in everything into that equation. So let's just pick data set number 1. Again, we can use any one that we want. The rate for that is 6 times 10 to the 5. We don't know what k is. N2 is 1.76, H2 is 2.19, and that's going to be squared. And all you have to do is solve for k.